for today is Peak 18 MSSP module in I2C mode part 2, that is the master mode. This is the third video on this topic. We have updated two videos on this topic. The first one, I2C bus protocol, that gives you the basics of the I2C protocol, and then PIC 18 MSSP module in I2C mode part 1, registers. Now in this video we have discussed the different registers for the I2C mode, that is the MSSP control register, SSP con 1, SSP con 2, and MSSP status register, SSP stat, then the serial buffer register, SSP buff, then shift register, SSP SR, and the MSSP address register, SSP add. So in today's video we are going to discuss the master mode of MSSP module in I2C mode. Let us start. Welcome to our channel Engineering and Technology for You. If you are not subscribed, kindly subscribe and press the bell icon so that you get notifications for our future videos on this topic. The topic for today is MSSP module in I2C mode part 2, that is the master mode. We'll start with the master mode overview. Now master mode is enabled by setting and clearing the appropriate SSPM bits in SSP con 1, that is the MSSP control register, and by setting the SSPEN bit. So here the SSPM 4 bits, they will decide the mode of the I2C. So 1011, now when we set this bit pattern 1011, will be going to the I2C firmware control master mode. So in this case the slave will be idle, and if the pattern is 1000, then it will enter the I2C master mode. So the clock will be determined by this formula, that is the F oscillator divided by 4 star the SSP address plus. So here the SSPEN bit, that is synchronous serial port enable bit. So if it is set to 1, then it will enable the serial port and it will configure the SDA, that is serial data, and the SCL, that is serial clock. These two pins, they will be configured as serial port pins. And in the MSSP hardware, if we are setting the TRIS, that is the data direction bits, equal to 1, when we set, if they are equal to 1, then the lines will be set as input lines. So both the lines, the SCL serial clock and the serial data, they will be input. So then let us go further. The master mode operation is supported by interrupt generation on the detection of start and stop condition. See, the start and stop conditions, they are very important in this I2C mode. So the transmission, data transfer will start with the help of this start, and it will stop with the help of the stop bit. The stop bit is P and the start bit S. They are cleared from a reset or when the MSSP module is disabled. So we have to enable them with the help of the what we have discussed just now. Then the control of I2C bus may be taken when the P bit is set or bus is idle, with both S and P bits clear. So when the bus is idle, at that time we can take the control of the bus, and then the data transfer will be possible. Then in firmware control master mode, user code conducts all the I2C bus operations based on the start and stop bit condition. So then this is the overview. Let us go into the master mode options. So once you are putting the master mode 1000 these bits, so the user has 6 options. First is assert a start condition on SDA and SCL. So we'll have to set the start condition. We already discussed the start condition in the first video, I2C bus protocol. Those who have not watched, kindly watch the previous videos on this topic, because this topic is little difficult to understand. So it is better if you watch those 2 videos and then watch this. Then the repeated start condition, that is SR. Yes is the start condition, SR is the repeated start condition. So that can be asserted on the SDA and SCL. That is the second option. So if the master wants to send more data, at that time this repeated start condition will be asserted. Then write to SSP buff register, that is the synchronous serial port buffer register. So initiating the transmission of data or address. So the data and address will be put in the SSP buff register. Then the fourth option is configure the I2C port to receive data. So if you want to receive the data, then you will have to configure I2C port in the receive mode. Then generate an acknowledgement condition at the end of receive byte of data. So that is another option. When you are in the receive mode, you will have to generate the acknowledgement at the end of the received byte. That is done by the master. And then the sixth option is generate a stop condition on SDA and SCL. So once the data transfer is completed and you get the acknowledgement from the slave, then you can the master can generate the stop condition, the SDA and SCL line. Then let us see the block diagram of I2C master in MSSP. So here we have these 2 lines, SDA and SCL. These are the 2 lines, serial data and serial log. And then we have these 2 registers are shown here. SSP buff, that is the buffer register, serial port buffer register, and this is the shift register. So we have discussed the details of this read and write operation of the buffer register and the shift register. So this is used for shifting the data, and the data will come on and it will be loaded into the buffer, SSP buffer. Then we have the start bit, stop bit, acknowledge generation. So this signals will be generated and they will be available on particular control registers. We'll discuss that in details, the acknowledgement signal, which bit will be used for getting that signal. So that is necessary for the data transfer. Then we have the start bit detect, stop bit detect, then write collision detect. So this is part of the SSP con1 W call this, and here the SSP status register and SSP control registers, their bits are shown here. In clock arbitration, state counter for end of, these are the signals which are necessary. So the bus collision, then the serial clock in, so this will be given as input here, and then only it will set or reset the particular bits of the control and status register. And this is the baud rate generator, that is for, and here we are going to use the SSPM 320, these bits. Just now we have discussed these bits, and the address, so the 7-bit address, so that will be used for generating the baud rate. And then we have the other circuitry for the, say, here the SDA data, serial data, that will be coming and detected. So in this way the master mode will work. And let us go to the master transmitter mode. So in master transmitter mode, serial data is output through the serial data line, and the serial clock output is available at the SCL. So the first byte transmitted contains the slave address of the receiving device. So that is the slave address will be 7 bits, and it will have a read write RW bit. So this RW bit will decide whether to write the data or read the data. So for transmission mode, so this will be logic 0. So that is for writing. Then each byte is transmitted, means 8 bits of data is transmitted, and then we the 9th bit we get the acknowledgement. So this is what we have discussed in the first video on I2C bus protocol. So start and stop conditions are output to indicate the beginning and end of the serial transfer. So always the start and stop conditions will be used for beginning of the serial transfer. Then you can see here writing to slave on the I2C bus. So in this case, to write to the I2C bus, the master will send a start condition. This is the first. It will send the start condition, and then it will send the slave address, which is 7 bit, and RW bar. So this, when this is 0, it is for the write. So this is the data sent from the master. You can see here from the master. As you can see, the details are given here. So the start bit is sent first, and then we have the address, slave device address, which is 7 bit, A0 to A6, that will be sent. And this RW bit, RW bar bit, if it is 0, that will be the write operation. Then when this is sent, the will get the acknowledgement from the device. After that, the register address, which is 8 bit, where we have to write the data, that will be sent. So B0 to B7, that is the register address. which is 8 bit. Here also same thing is shown here, data. Then again we get the acknowledgement for that. That will be the 9th bit, and then we'll send the actual data byte to register, which is where we are given the address here. So that will be written. So data is sent, and then we get A or A bar. So if we get A bar, then that means we have to stop. So P bit will be sent by the. So all these the signals which are sent by the master are shown here in the dark, and the slave just sends the acknowledgement. So once we get, master will terminate the transmission with the stop condition. So when the stop condition is achieved, the transmission will be terminated. You can see the timing diagram or the waveforms for this. So this is the start condition. So in the start condition we have SDA and SCL. So this is going from high to low, and at that time the serial clock, it is high. So that is the start condition. So once this is achieved, then we are sending the address. So 1 to 7 bits, that is 7-bit address, and this 8 bit is the RW bar. So in this case it is if it is 0, it is the write operation. Then we have the 9 bit as acknowledge. Then we have the data, which will be again 8 bit. So here in this case we are considering the address of the register to which we have to write the data, and then again we get the acknowledgement as the 9th bit. And here this is the actual data is sent on the lines SDA. Here we are, here the data will be sent, and again we get the acknowledgement. And then the stop condition, here it is just reverse. So low to high transition of the data line, serial data line, when the serial clock is, there is the stop condition P. So this is achieved, then the data transfer is completed. So this is the basic I2C protocol, and now we are trying to have the MSSP, using MSSP, the master mode. So this is the typical transmit sequence steps. So the first step, the user generates the start condition. So always the protocol will start with the start condition by setting the start enable bit. Now this SEN bit, it is in the SSP con 2, that is the control register 2, bit 0. So you can refer to the previous video for the details. Then the SSP interrupt flag is set. So that is for the interrupt enabling. Then MSSP module will wait for the required start time before any other operation takes place. So we already shown the diagram, timing diagram. So that is with reference to that. Then the user loads the SSP buff with the slave address. So here the slave address is 7 bit. So that will be loaded, and this address is shifted out to the SDA pin until all bits are. So that's why the shift register SSP SR shift register, that will be used here. Then MSSP module shifts the acknowledgement from the slave device. The slave will send the acknowledgement, that is the 9th bit, and it will be coming to the MSSP module. So it will be shifted and it writes its value into the SSP con2 register bit 6. So this is very important. Here the bit 6 for SSP con. So that is the acknowledge status bit. Here you can see. And if it is 1, that means acknowledge was not received from the slave. And if it is 0, acknowledge was received from the slave. And depending on this bit, the MSSP module generates an interrupt at the end of the 9th clock cycle by setting the SSP I of bit. That is the synchronous serial port interrupt flag. So the data transfer is done with the help of then next, the 7th step, the user loads the SSP buff, that is the serial port buffer with the 8 bits of the. Then again the data is shifted out on the SDA pin. So because this is a serial communication, one by one the bits will be going on the data lines, that is the serial data line, until all bits are transmitted. Then the 9th step, the MSSP module shifts in the acknowledgement. So once we send the data, we'll get the acknowledgement from the slave device. So again this value will be written into SSP con2 register bit 6. So just now we have discussed the bit 6. If it is 1, we are not received the acknowledgement. If it is 0, acknowledgement. Then again the MSSP module generates an interrupt at the end of the 9th clock cycle by setting the interrupt flag bit, SSP interrupt flag bit. Then once this is done, the user generates a stop condition by setting the stop enable bit. Now this bit is bit 2 in the SSP con2, that is control register 2. So you can have given the description here. So this PEN is stop condition enable bit. So if it is 1, then initiate stop condition on SDA and SCL pins. So initiate stop condition means the SDA pin will go from low to high and SCL pin will be held high. So that is what is the stop condition. So this will be done, and then again the interrupt is generated once the stop condition is complete, and this means the data transfer is completed. So in this way, you have to understand that we are making use of the MSSP in PIC 18 for the transfer of data using the I2C bus protocol. So that's why this bus protocol is a 2-line protocol having the 2 lines SDA and SCL. So these 2 lines are used, and the protocol I2C bus protocol is implemented using the MSSP PIC 18. So then we'll just have an overview of the receive mode. So in the master receive mode, the first byte transmitted contains the slave address of transmitting device and the RW bit. Now in this case the RW bit will be 1, logic 1, so it will be high. So that indicates that the mode is in the receive mode. The first byte transmitted is the 7-bit slave address and the this RW bit. Okay. Then the serial data is received via this serial data line, and SCL will be used as the clock. and again we receive the serial data in a byte form, 8 bits at a time. Then after each byte is received, an acknowledge bit is transmitted. So the master will transmit the acknowledge bit now, and then here again the same thing, start and stop conditions indicate the beginning and end of transmission. So if the end of, we want to have the end of transmission, then stop condition will be put on the SDA and SCL line, and the transmission will be terminated. So this is how the master mode will work in the transmission and the. So with this we come to the end of this video. If you have any queries, you can contact me on Facebook, Twitter, Gmail or Instagram, or on the website also you can put. Then if you like the video, press the like button, share with your friends, and subscribe to our channel Engineering and Technology for You. And don't forget to press the bell icon, because I am going to upload some more videos on this topic and the MSSP in SPI mode. We'll take up the EEPROM problem interfacing. Then thanks for watching. Have a nice day.